Good afternoon, guys. Today, I'm just going to do a few examples on linear momentum and collisions. It's a more simple topic, and it doesn't involve a whole bunch of equations. And some situations are going to be similar to the ones we have studied before in Newton's laws and in conservation of energy and work. Now, this video will be uploaded in Canvas as usual, and it will be a two-part video. Today I will just talk about linear momentum and collisions, elastic and inelastic. And next video we will talk about center of mass. Once we do that, you will have all the tools to start solving the assignment. I will also place a video to help you on the assignment and also for the test on this chapter. As you can see, we have a few more weeks left. I mean, we are still on the beginning of April, so that's not bad. I will try to upload a video on these two topics in the next couple of weeks. And based on the pace of the class, I really want to get at least to week 12. At least these two topics, we're going to try to cover them. If not, let's try to get to week 12. Okay? So make sure you are catching up with the homework. Make sure that you are finishing the tests. Right now, you guys should be working on a work and energy quiz, and the test will be uploaded once we finish week 10, which is linear momentum and collisions. All right. So what is linear momentum? Linear momentum is a vector. So it's another vector quantity that we are going to label with the letter P, since L is used for many other parameters, right? Length, for example. So this is defined as mass times velocity, not speed, velocity. So the direction is going to be important, right? There. So we are going to care a lot about the direction. The units are kilograms, meters per second. All right. Those are the units. And we are going to be looking at certain conservational laws. We have done conservation of energy. There is also this idea of conservation of momentum based on an isolated system of particles where only the internal forces are acting, like I'm drawing here, F1, F2. So what we know is that in this isolated system, the sum of forces in equilibrium is 0. But we know that a force is mass times acceleration, which is the first derivative of velocity in respect of time. And the same happens with this. And this is M1, this will be M2. But if you remember from calculus, we can combine those two, right? I mean, the derivative of v respect of time is the acceleration. If I put a derivative of mv, m is a constant, so I can just write it like this. The total derivative respect of time of m1v1 plus m1 m2 v2. And I can do that because this is an addition. I use the addition rule. And that's equal to 0. So you know what that's telling you? That's telling you that this quantity is constant, right? The derivative of a constant is 0. And m1 v1 will be momentum 1. So momentum 1 plus momentum 2 is 0. So what we get from here is that momentum 1 plus momentum 2 is 0. And this is going to be, and you have probably already experienced this. When you say you catch a ball, or you throw a ball and then you receive, or if you have seen in shooting ranges or in movies, you see that when you shoot a weapon, you receive action reaction, that's right. But if you use the conservation of momentum, then you will see that the idea behind that, or the physics behind that, is that the momentum of the bullet, right, is equal to the momentum of the rifle. The difference is the mass. The bullet is what, 5 grams, 10 grams, but a rifle can be what, 15, 10 kilograms. So it's very heavy. So the bullet goes at a very high speed, but the rifle will not. It will proceed just like this. That's because of this, right? So in an isolated system, that is the idea. And thanks to that, we can explain a whole bunch of natural interactions. We can use it when you play billiards, for example, right? Because collisions is the direct application of conservation of linear momentum. Remember that we're talking about linear momentum. So particles moving in the plane at vertical or horizontal speeds. We are not discussing yet particles rotating. So here it is, and here is a demonstration as well. And that's the definition of linear momentum, okay, which is the product of the mass times the velocity. And then, well, we can derive, thanks to this, we can also derive Newton's second law. Because if you remember, we have that force is mass times acceleration. The other version of Newton's second law is that the first derivative of momentum in respect of time, when there is a force acting on a body and moving the body, right? The first derivative of momentum, that's equal to the force. Right? How do I know that? Because if you analyze this part, the left-hand side, the derivative respect of time of momentum is mass times velocity, which is mass times the derivative of velocity respect of time, which is the acceleration. And what is this? That is that. And what is all this then? Newton's second law. So that's another way of proving it. And that's here. Remember that momentum is a vector that can be written in 3 directions, since the velocity can go in X, Y, and Z. Okay? Objects that have equal kinetic energies do not always have the same momentum, because the kinetic energy depends on mass and velocity. An object and another object, they can have the same kinetic energy, even if the velocities are different, because the masses may be different, right? But if you have objects with equal kinetic energies, that doesn't mean that they have the same momentum, right? Because they may have different speeds and different masses. You just tabulate, so they have equal energies. All right? So there wouldn't be enough information to tell in this question. Okay, now let's go in a real life example, right? If you're in the gym and they throw you a ball with some speed, you may be able to catch it. That's easy. But now let's suppose they throw you those medicine balls, those very big, massive balls, right? What would be the best way to catch it? With the same speed? No, that would be very hard, right? Because you can throw a ball very fast, and you don't want that with a medicine ball. With the same momentum, I mean, if you have a baseball, which is, let's suppose, 3 kilograms, 2 kilograms, 2 to 3 kilograms, and you throw with 10 meters per second, right? That would be 30 kilograms meters per second momentum, right? But if I give you a medicine ball, that is 30 kilograms now. That means that the speed has to be 1 meter per second. So that's convenient. You can have the medicine ball with the same momentum, because that means that the very big mass will counteract the velocity. So then the velocity will be very low. What about the same kinetic energy? Similar, but it's more convenient with momentum. All right. So same momentum will be the easiest, then energy, and then obviously same speed, right? So that's that. We have already done that. If you have particles interacting in an isolated system, the action-reaction, which is F12, F21, the derivative respect of time of those moment of the additional momentum is equal to 0. That is a direct consequence of Newton's third law, if you think about it, right? So whenever two or more particles in an isolated system interact, the total momentum does not change. For example, a collision, all right? An isolated system can be illustrated like that. No external force acting. So that's very crucial. This is for an isolated system where no forces are acting. As soon as you have a force acting, then you have a change on velocity. And yes, there is a change on momentum. But that change on momentum is proportional to that force, right? As I just wrote on the board, that's how we derive Newton's second law, all right? But for an isolated system, no force is acting, the momentum, the change of momentum is equal to 0, as you have in here. Okay, a 60 kilogram archer is in a frictionless ice, okay, and he's gonna fire an arrow with certain speed. With what velocity will the archer move across the ice? All right. So that's a very typical example that you may get in a quiz. If you have an archer with mass 60 kilograms and he's standing on a frictionless surface, right? Then if he shoots an arrow which has mass 0.03 and a velocity of 85 meters per second, we know by just inspection that the archer will receive with some velocity v. But the mass of the archer is 60 kilograms. So since there is no other forces acting in the system, the momentum of the archer plus the momentum of the arrow has to be equal to 0. Remember that we're talking about velocity. So the arrow has positive momentum. The archer will have negative because of that v. So the archer will be minus 60v plus 0.03 times 85. That's equal to 0. Right? Later, you will learn that a very easy way to do this as well is by saying that the momentum of the archer is equal to the momentum of the arrow. Since you only have two masses or two objects interacting. The magnitude of v, so the magnitude of the velocity of the archer, I get 0.04 meters per second. So yeah, he won't receive with a lot of speed, right? But still, as you can see, that's because of the very large mass of the person in comparison with the mass of the arrow. All right. So that's what they do in the slides. Now, what happens if you throw the arrow with certain angle? So now let's change this part. And let's say that the arrow is being fired or shot with certain angle theta. And it's the same mass. So if we understand the situation, we know that vertically there is no motion that we really care. For the archer, for the arrow, yes, there is this V85 cosine theta. And 85 sine, but for the archer it doesn't matter. So now you use this component. Minus 60 times the velocity of the archer plus 0.03 times 85 cosine theta. That's equal to 0. If I give you the angle theta, you can find the velocity now. All right. All right. Let's talk now a little bit about impulse. Now we know that there is another way to write Newton's second law, where is the net force acting on a body is equal to the first derivative of momentum respect of time, right? So if I do the algebra, I can move the differential of time to the right-hand side, as they show you in the slides, and then you can perform an integration, right? Because you have that sum of forces, or the net force acting on a body, is equal to the derivative of momentum respect of time. If you multiply by dt and apply the limit, you will get that the sum of forces dt equals to d momentum. If you integrate on both sides, then this is called the impulse. And that's equal to the integral of dp, which you know what give you the change on linear momentum. But what is impulse of? Let's not forget that impulse is an integral. Is the integral of the net force times dt. So if you have a graph of force versus time, I'm pretty sure you will see this graph in the lab at some point. It looks like this. Momentum after, momentum before a collision. But that doesn't matter for now. The force, the area under the curve, this area is equals to the impulse. All right. So that's the idea behind impulse. As you can see, there's not many difficult concepts, and there you are. Okay. Of course, in this case, if you're applying this, not the integral part, you're assuming that the force is constant, but you know that's not always the case, right? So that's why, in general, we define it as an integral, and then we have that the change in momentum is equal to the impulse of the net force acting on the particle. All right. Okay. Two objects are at rest. Object 1 has a greater mass than object 2. You apply a force constant to object 1. it accelerates through a distance d. Then you apply the same force to object 2, and you make it accelerate the same distance. Which extensions are true? Okay, if you apply the same force to any object and you move it the same distance, the work applied will be the same. And you know that if the work applied is the same, the change on energy is the same. So what we can see here is that kinetic energy is equal to the kinetic energy of 2. Because it says that they are at rest. So the final kinetic energy will be the same for both masses. That's because the force is exerting the same work, since they are moving the same distance. What's not true is that the velocity won't be the same, right? Or we don't know. So what can we say about momentum? Actually, we know. If one mass is less than the other, that means that that mass will have more acceleration. More acceleration means more speed. That means that the final velocity, of object 2 will be greater than the final velocity of object 1. Because by Newton's second law, the net force equals to mass times acceleration. If the mass gets less, the acceleration gets higher. So what we can say is that the momentum on one, right, will be greater than the momentum on 2. Wait a second. Which is the matter? So kinetic energies are the same. But the mass on 1 is greater than mass on 2. So momentum, mass times velocity. Yeah, momentum on 1 will be greater than momentum on 2. Yeah, that's right. Okay, that's because even though the object 2 will have more velocity, the mass on 1 is greater. All right, so let's see what we have here. The change momentum is less for object 2. Yes, because force is equal to change of momentum. And momentum is mass times velocity, right? Since the mass is constant, then yes, since the change on velocity on 2 is greater, right, then you will have a greater momentum on 1. All right, that can be a bit tricky. You may want to give some numbers to understand this. I will probably give, well, you know, it's 0 speed, just give a force of 50 newtons and just give a distance of 10 meters and try to solve the problem. In fact, I think that's the best way you guys can understand these conceptual questions. Just give numbers, all right? Object 1 can be 5 kilograms or 10 kilograms, object 2 can be 5 kilograms. And then that way is much easier to understand this problem. All right, so you don't get confused with the variables there. Okay, so we can skip this for now. Okay, let's see what this is. An automobile dashboard, seat belt, and airbag are each used along in separate collisions from the same speed. In terms of impulse, run this. So they will have the same, right? They will have the same because the impulse only depends on the change of momentum. And since the car is just one object, one system, the seat belt, the dashboard, and the airbag, they all belong to the same system. So the change of momentum will be the same for the three objects, then the impulse will be the same. Okay, so let's take a look at a problem. All right, don't worry guys, I know that some of these problems are very simple. I will do the more difficult problems when I do the video on the web assign, all right, and I will help you and I will give you some of the tricks that you have to understand, especially for collisions. This can be a little bit more complicated, but it's all about understanding the situation. For example, here, remember, we are talking about velocities. So we care about the direction. As you see in the picture there, they give you a mass of 1,500 kilograms that is colliding with a wall. All right. The initial and final velocities are -15I and then 2.6i as it bounces back to the right. And the collision lasts for 0.15 seconds. Find the impulse, and I'm going to add, find the average force exerted on the car. Okay. So how are we going to do that problem? Let me just close some videos here. The change of momentum is the impulse. But momentum is a vector. So we have to be careful with directions. You can put here the wall. You can put, or you can write minus 15 going to the left. And right after 2.6. And the mass of the car right? Impulse is change on P. By the way, yeah, impulse also vector, right? But let's put here P final minus P initial. P final is that. What's P initial? Minus 15 times 1500. Minus and minus plus. And if you do the algebra, you factorize this times 17.6. And that will give you 2.64 times 10 to the 4 kilogram right? How do I find the net force, the average force? Impulse is the integral of force dt. That's the analytical definition. But for a situation like that, a very macro type of situation, right? Your impulse is equal to force times the change on time. And the change on time is, they're giving a problem, 0.15 seconds. So your force will be that impulse divided by 0.15, which will give you 1.8 times 10 to the 5 newtons. Also in the positive x direction. So that's easy. It's simple. That was the first example where we have to deal with collisions. So impulse and momentum can be applied in different situations. The situation we're going to look now is a situation with collisions in one dimension, okay? In the slides, they give you two pictures. This one that we're going to deal now, and then this one that we apply a lot in quantum physics, which is collisions in multiple dimensions, at least in 2 dimensions. All right? So here is where you have an event where particles get close to each other and interact by a meaning of a force. That's why they bounce back at different directions. We're going to assume that the interaction forces are much greater than any external forces that are acting on the system. So we can use the impulse approximation. We are also going to remember that for an isolated system, the change of momentum is constant, is zero, sorry. So we have that, right? So if you have two masses coming to each other with different velocities, after they collide, the momentum before and the momentum after the collision will be the same. All right? And that's what you have there in the equation. Now, this is applied for any sort of collision. What you're seeing right now is what we call a total or perfectly inelastic collision. The major characteristic of that collision is that the bodies stick together after the collision. And we're going to be doing quite a few exercises like that. But that's not the only type of collision. We also have the elastic collisions. So for the elastic collision, let me show you on the whiteboard what do I mean by that. All right. Okay. And after this, we can start doing some problems on collisions. And most of those problems, they use the same principle. Conservation of momentum for inelastic or perfect inelastic. And for elastic collisions, however, they use an additional conservational law, which is the conservation. Because the elastic collision has a very important property. In an elastic collision, the change of kinetic energy of the system of masses is constant. So let's say I have two masses here. M1 moving with velocity V1 initial, and you have M2 moving with velocity V2 initial. This is before the collision. But now after the collision, so they collide. Right? And then as you expect, let's say M1 is moving to the left, V1 final, this one is moving to the right, V2 final. The conservation of momentum is will tell us that the momentum before, after here, is equal to momentum after. So M1, B1 initial plus M2, B2 initial equals to M1, B1 final plus M2, B2 final. All right. That's nice. What other thing do I know? What I know from elastic collision, and by the way, if you guys have done gases, you should know that an elastic collision is how we model ideal gases. All right? So we assume that the particles are bouncing with the walls of the container and between each other, and there is no loss of energy. That's why it's called an ideal gas. The other conservational law is that the kinetic energy before the collision is equal to the kinetic energy after the collision. The thing about this is that we can actually do this, remove the halves, and combine look what I can do. I can combine V1 final with V1 initial. M1 V1 initial square minus V1 final square. And then I can do this. This can go to the other side. Why do I do that? Because this is a difference of squares. So this equation, I can have it like this. That is equal to right? You can see there, let me see. Right, you can see this in here. I rearrange and I get this. And I do that because when I apply difference of squares here, I get V1 minus V2 times V1 plus V2. So what I'm gonna get is this. If I erase this, let's expand this, and let's use another color. I will get this, guys. If you do the algebra, M1 V1 plus V1 initial plus V1 final times V1 initial minus V1 final, that's all equals to M2 V2 final minus V2 initial times V2 final plus V2 initial. Now, why am I doing that? Because look, M1 V1 minus V2, M1 V, so this is equal to V2 minus V to this. So I can cancel all this. It's equal. And you know what I get? I get that V1 final, this is what I get. The consequence for an elastic collision, only for the elastic collision, right? V1 initial plus V1 final is equal to V2 initial plus V2 final. This only is true for elastic collisions. So what are the two rules that you need to use for elastic collisions? Let's erase all this. The two rules are the conservation of momentum, so I'm gonna rewrite it here, M1 V1 initial, remember it's velocity, plus M2 V2 initial equals to M1 V1 final plus M2 V2 final. I need this. And the other rule will be this. But you know what? I can write it like this though. V1 initial minus V2 initial equals to V2 final minus V1 final. Or in some textbooks, what they do is this, minus V1 final minus V2 final. So 1, 2, 1, 2. That's what they do. So V1 initial minus V2 initial is equal to minus V1 final minus V2 final. Only for elastic conditions. All right. So that lots of variables. And the thing is that, guys, do not make the mistake when you are doing this. Here is the proof as well of memorizing this. This will be the worst mistake you can make. Because as soon as I change the numbers, that won't work. It's sort of like what we did in projectile motion. Don't memorize. It's not going to be good if you memorize this. And look at this. It's too much. So don't ignore these two slides. Understand this and this. All right. Okay, what's here? What condition will make that after objects stick together in a collision, the final kinetic, so they don't move, the momentum has to be equal but in opposite directions, because the momentum initial is equal to momentum final, right? If you want the momentum final to be zero velocity, which means zero kinetic energy, you need to have the initial momentums be in opposite directions and the same magnitude. So 1 plus minus 1, 0. So that would be the answer for that one, right? All right, this is how you do some of the problems. This for now, let's see here. An 1,800 kilogram car at a traffic light is struck from the rear by a 900 kilogram car. The car becomes entangled, so they stick together, moving along the same. Okay, if the smaller car were moving at 20 meters per second before the collision, what's the velocity of the entangled cars? Okay, so the first car is stopped. That's very easy, right? For a perfectly inelastic collision, those are going to be the easiest problems to solve, because you don't have to worry about any of this. But don't worry, we'll do an elastic collision. And then a problem using energy, and that's how we will conclude this video. So if you have a mass of 1,800 kilograms, which is at rest, right? And then you have, and then you have another mass, which is going to collide or is going to have a collision with that mass. All right. And then you have a mass of 900 kilograms now. And this mass is going to collide with the speed of 20 meters per second. And they are going to be stick. So it's a perfect inelastic collision. What you should do is this. 1,800 times 0 plus 900 times 20 equals to, on a perfect inelastic, they stick together. So 1,800 plus 900 times 50. This would be 18,000 2,700 divided by 9, 20 divided by 9, 3, 20 divided by 3 is around 6.6 meters per second. That would be. All right. So that's easy. That wouldn't be much of a problem. Let's do an elastic collision now. So, what is a typical elastic collision problem? And this is the thing though. The way I'm going to solve the problem is the way that you will see it in textbooks as well, but you can always come up with your own strategies. You have to do a graph of the problem because it will help you. And yes, you have to be careful with the directions. So let's say I give you a mass, two masses. One mass, it's going to be 4 kilograms, like that, and it's going to be moving at 10 meters per second. And then you have another mass of 3 kilograms, which is going to be moving to the left at 12 meters per second. That's before the collision. After the collision, let's say you have this, and this. V2 final, V1 final. You want to find both velocities. So it doesn't seem like you have enough information, but you do. The conservation of momentum is an easy one. So this is before, after, right? So let's put here the conservation momentum. So momentum initial will be 4 times 10, positive 10, minus 3 times 12. Why minus? Because that velocity is negative. And that will be equals to M1 V1 final plus M2 V2 final. Well, I know M1 and M2. Okay. Now we have to use the conservation of energy, but we already know, right? It was V1 initial plus V1 final equals to V2 initial plus V2 final. Or the other way, V1 initial minus V2 initial equals to minus V1 final minus V2 final. V1 initial is 10. V2 initial is minus 12. So this will be 10 minus 12 equals to negative V1 final minus V2 initial. Or V2 final, sorry. This will be 22 equals to V1 final, V2 final, because I want to distribute a minus. So 40 minus 36 is 4. So what I have here is one equation. I have 4 equals to 4 V1 final plus 3 V2 final. And 22 equals to V2 final minus V1 final. All right, so I have a system of 2 variables and 2 equations, right? You see here? So let's let's finish it here now. Four equals to 4v1 final and here I have 22 v2 final minus v1 final. I'm going to multiply this equation by 4 because I will get 88 4v2 final minus 4v1 final. So now I can erase this. And then if I add these equations, 4 plus 88 is 92. 4v1 final, 4v1 final, 4v2 final, 7v2 final. And that will give me almost 13, right? So V2 final will be 13 meters per second. And that's perfect, guys, because look what I get from here. So that makes sense. The velocity for the second ball is going to the right. Almost with the same speed, a bit more because this 10 gave it an impulse, right? But the force still. Now, what about V1 final? V2 final minus V1 final. V1 final goes here. 30 minus 22 minus 9 meters per second. So there you are. Perfect. V1 final is going to the right. It's going to the left, sorry. V2 is going to the right. Pay attention. This problem will probably be very similar in exam, guys. Look, I'm going to stop it right now there. I will place another video doing a couple more problems similar to the ones in the web assigned, but this one should help you a lot. I will do one combining energy with collisions, and then we'll do center of mass. All right. I hope this is helpful, guys, and I will see you guys on the next video for you guys right after this.